Yes. Okay, thanks a lot. Now we're going to switch not from field, like it's still ultra-fast magnetism, but from experiment to theory. And actually, I'm very happy, first of all, to be here and to be invited to this work. And I would like to give my perspectives of like potential of altermagnetism in ultra-fast magnetism from the side of theory. But just to start with that, a little bit of general motivation of what we try to do and where we think that theory can help. So the problem that we see, if we think about what is there in technology, is that we can switch magnetic bits, like very small magnetic bits down to 10 nanometer. And we can also do that like on nanosecond time scales. But if you even think about theory, pushing this to like nanometer or even sub-nanometer and femtosecond time scales, we very quickly realize there's nothing to do. And if you look at experiments in this regime, like the ones that Davide was just showing, they show you results which are very hard to understand with conventional theories which rely on thermodynamics. So this is the problem that we try to address. What kind of simple and simplified descriptions can we develop there? And our favorite tools for that are numerical simulations and analytical theory. And the problem that I focus on today, like which was already very nicely introduced by Davide, is the two-magnon physics. So that means, so this is one way to approach this ultra-fast nanomagnetism, because the wavelengths of these magnons can be made very short. And why then two-magnon? Well, exactly because in that case, this is experimentally very convenient because you can still come with your ultra-short pulses, light pulses, which have very long wavelengths as compared to lattice spacings, but still you can excite magnons with a wavelength which is just the distance between two atoms. And this is also a very well-known transition, like in equilibrium, like spontaneous Raman scattering has been done since the 60s on this, and it can be triggered by ultra-short pulses, and we have seen already nice examples today. And then I would like to connect this problem to altermagnetism. So why is that actually maybe an appealing way to also explore altermagnetism? Well, first of all, the magnons at the edge of the Brillouin zone, they are dictated by the exchange interaction. For the majority of cases, we can completely ignore that there is anisotropy. The energy is just given by exchange. And this magnon dispersion itself is, of course, governed by the lattice structure. So we deal with a problem which concerns the lattice symmetry and exchange interactions, which are exactly the ingredients. If I read the papers of altermagnetism, they deal with spin symmetries in the exchange approximation. So potentially there is interest and there may be observable effects of altermagnetism on ultra-fast timescales if we focus on magnons at the edge of the Brillouin zone. Okay, that's the problem that I would like to understand, but then I must face the fact that even in high symmetry crystals, say just for the rest of my talk I will focus only on cubic crystals, even there we don't understand well the physics of the dynamics in space and time of these magnons at the edge of the Brillouin zone. So what are the fundamental questions that we want to understand about this two-magnon mode? So if we excite it in time, we want to be able to isolate what is the symmetry of this excitation. And we want to understand what is the observable, how can we detect such short wavelength magnons? So what is the microscopic observable that tells us that we look at that? And then these are two magnons. We talk colloquially that these are counter-propagating. But if you think about it like just intuitively, you would expect there may be no propagation at all, because magnons at the edge of the Brillouin zone, the group velocity is practically zero. So why would it propagate at all? Okay, so this is what I try to understand. And if you want to understand that, you quickly realize that even for simple models, this is not a simple problem to solve, because we basically cannot use all the approximations that we like to use. We are with short wavelengths, so that means we cannot expect that macro spin approximation works well. We excite pairs of magnons, so this fundamentally goes beyond single particle picture. And typically in the literature it's known we don't excite a single pair, we excite multiple pairs, so we deal with a superposition of two particle states, and that means automatically that we get entanglement, so we cannot ignore quantum effects. So it's really something else. and we need to understand what it means. So this is what I will try to explain to you today, how far we came with that from the side of theory. So I will first introduce a minimal model just for cubic antiferromagnets, and then present some methodology. That's for this talk not so important, but nowadays we can solve these quantum models very accurately with machine learning. And then we use that to study this dynamics in space and time of these magnon pairs. And based on the intuition that we developed from these models, we developed some analytical theory, and together with experiments then we try to understand what are these selection rules. Okay, so that's the plan for today, and then the model is just the absolutely minimum model for magnon pair physics is the two-dimensional antiferromagnetic Heisenberg model, so just a square lattice. And then what do we know? How can we excite these things? The mechanism for that is the perturbation of exchange. And here is something important, like this perturbation of exchange feels the bonds at which this, between the electric field and the electric field of the light pulse, or the polarization of linear polarized light, and the exchange bonds in the crystal. So typically, you do not excite all bonds in the same way. If you would do that, then you would just change the total exchange energy, and you would not expect any dynamics, because it's just a scalar change of this Hamiltonian, and you cannot excite dynamics with that. But in this case, if it's like macroscopic, so it's a long wavelength excitation, but it's still anisotropic in space. So then, how could we understand this a little bit more microscopically? If you just look at the effect of this term here on the top right, then the term which generates you magnons is this S plus S minus term. So here on the left you see a picture of a, say, classical antiferromagnetic Niel state, and what such quantum operation does is you just interchange these spins. And this also tells us that it's an exchange process, so that would be inherently quantum. But even if you would do such an exchange process in a classical antiferromagnet, after that you would not expect any dynamics at all because there is no torque. So we cannot use our intuition of like that we're used to, just derive some phenomenological equation and say, okay, now I have some generalized torque, and from that I can understand the symmetry of the effect. This doesn't work for two-magnon, and so we need something else. Okay, so then let's try to do that. So what the approach we took after the, say, analytical studies, we wanted to do this more rigorously, and that's why we just used these two Hamiltonians. So this ground state Hamiltonian and this, the way we perturb the system, and try to solve the problem exactly for which we use this neural network quantum states. So for theorists in the room, I can just explain you why I'm so excited about this, because for large magnetic systems, if you want to simulate quantum effects, there are basically no good methods. And now with this new machine learning approach, we have something which we think can really operate as the atomistic spin dynamic simulations that we are so fond of if we want to simulate metals, also in the quantum regime. And the reason is that this is a variational ansatz, and as any variational ansatz, you can do the standard tricks that we use, like for example, for me, the time-dependent variational principle is very important. But now this ansatz is not biased by some intuitive model that you have, or you think, or this kind of effect is dominant. No, you just take this wave function as a black box, and you give it a spin state, it gives you an amplitude, it gives you a phase. And this can be arbitrarily complex, but that's the beauty of machine learning. There's universal function approximation theorem, so in principle, any complex function you can approximate with this neural network, and that means we have a practically unbiased approach, which is systematically improvable. And here you see the result which make me excited. You see that you can actually approximate this ground state energy with increasing accuracy. So that's why we jumped on this problem, or we started to use this method, and we were actually the first group that in the world that was able to calculate quantum dynamics in two-dimensional Heisenberg antiferromagnets. And the results of that I'm going to show now. So what we do is so we still start with this Hamiltonian, and we make some perturbation to that. In this case, the perturbation was always along the vertical axis. And then you see propagation patterns, which I will show in a minute. But now I have to, before showing that, I have to explain you what we actually measure here. So if you just look at this from the theory side, you say, okay, this is a rotationally symmetric Hamiltonian. It just contains the product of two spins. And also this perturbation is rotationally invariant. It's also translationally invariant. So we cannot expect from the beginning that there is any macroscopic magnetization which appears, right? Because we just don't have this in our model. And you can say, okay, then you make your model better. But okay, this appears to be the model that everybody has used to explain spontaneous Raman scattering. So why should we try something else for this ultra-fast regime? So then that's why we look at the spin correlation as main observable. And okay, in principle, you would average that over the system, but because you have translation invariance, every other spin is the same. So now, you can, this correlation function for equivalent distances is only depending on the difference, and that's the consequence of translation invariance, so you can just calculate it for one correlation. And then you get a propagation pattern which looks like this. So you see here now, these are the vertical bonds, these are the horizontal directions, and then you see a propagating wave front which is propagating in the system. So that's just the propagation of correlations, and of course, this will tell us something about how magnons propagate, right? Because the propagation tells you, like, okay, how long does it take as a function of time before the spin at side I is correlated with the spin at side J, and if there is only magnon in your system, then this arrival time will be dictated by the magnon's velocity. And we see indeed something propagates, and what propagates is actually very anisotropic, which was a surprise for us. When we first did it, actually, we thought maybe this is just some interference effect, because still these neural network quantum states allow us to simulate big systems, but in fact, it's still not big in terms of macroscopic variables. This is something like 12 by 12. Nowadays, we can go to 20 by 20 or even 30 by 30. But in the first result, we thought it was just interference because of finite size effects. But then we started to think about this deeper, and actually we can understand this anisotropy of this propagation pattern very well. And you can just rewrite, so I will show you a little bit of formulas. If we rewrite this perturbation in a slightly different way, you see that the prefactor just has a cosine 2 phi dependence. And then you can argue, okay, if I would do just linear response, I would get this 2 phi dependence in front of my expectation values for these correlations. And that means if I then rotate the lattice together with the polarization, nothing should change at all. And from that, we can immediately understand that the correlations along Y should have opposite phase than the correlations along X. So this is also what you see here, like along Y, this is red, along X, this is blue. So when the propagation along X is first oscillating down, the correlation along Y is first oscillating up. So this is kind of D-wave symmetry, and this is also why I asked the question, like in response to the talk of Alexei, like, I don't know, this is kind of D-wave symmetry. I don't know if you can call this an altermagnetic state or not. I would be intrigued if you call it like that, but at least it has this symmetry. Of course, this is in real space. And if it would be altermagnetic, it would be the fastest way to come from an antiferromagnetic to an altermagnetic state. So that's just food for discussion. Anyway, now we understand what is this symmetry of this space-time propagation if we look at this excitation of magnon pairs. And then we also went on to do something more. So we wanted to understand what now is this velocity of propagation. So we looked only on, at the correlations along the x direction. And then you see this light cone type propagation. And to extract the velocity, what we did is we just plotted these arrival times of these maxima as function of time. So I mean, we plotted the times as function of space. So this is space now, this is time. And here you see the expectation, this dashed line that you expect just from linear magnon theory. So then we would expect twice the velocity of the highest magnon velocity that is there, because one magnon goes to the left, the other to the right. And that means that the velocity is twice that velocity. But in fact, what we find is that the slope here is higher than any magnon velocity that you have. So it's actually 40% higher. And that means that we find that spin can propagate faster than any magnon can do. And that's why we term this supermagnonic propagation in spirit of supersonic propagation, which is faster than the speed of sound. Okay, so how can it be, and how can we understand that something propagates in the first place? Because we were thinking that we deal mostly with magnons at the edge. Well, then we went to some approximate theory, which is the Schwinger-Boson mean field theory, which allows us to capture effects of magnon-magnon interactions in an approximate way. And then we can easily calculate this response of excitation of magnon pairs in reciprocal space and as a function of frequency. And then we see that we actually get two modes. One is a propagating two-magnon peak. And we always see it, and you may wonder, why do you see it? Well, indeed, the amplitude of this propagating modes is small as compared to what we have at the edge, but it's there. So what we understand is that, in the sense that we just excite a whole collection of magnon pairs, not only those at the edge, but also those in the entire Brillouin zone, and those at smaller wavelengths, they really propagate, and that's what we see. But in addition, there's this blue mode, there is this quasi-bound state. So it's a bit reminiscent to what people discussed in one-dimensional systems, where you have two magnon-bound states. So this is not a bound state, but a quasi-bound state. And actually, this competition between these two modes is what is the origin of this supermagnonic propagation. Okay, so now we understand something propagates, and something can propagate even faster. So now we would like to come with some simplified theory, and the thing, and something which we can also apply beyond 2 dimensions. So that's why we started to develop on that, actually expanding on the work we did together with Olena and Davide. And instead of focusing on describing a magnet in terms of two vectors M and L, we suggest now, let's just write this two-magnon physics directly in terms of spin correlation function. And that means we can just write the Hamiltonian in this way. It's just a sum of correlations along different bonds. And also the light-matter interaction for the geometry that I show here. You can write it just in terms of spin correlations. And then we can do the thing that we always do. If we describe magnetization dynamics, we always do some linear response, which means we think of small deflections as compared to a collinear ground state. And now we do the same. So we start to expand these spin operators just in terms of Sx and Sy terms. And then it's interesting, you can identify 3 different contributions. So now I also transformed already to reciprocal space. So one which is the sum of symmetric contributions, one is the difference of xy contributions, and one is looks more like the occupation of these magnons. And then if you just work out the commutation relations for spin operators, or equivalently what we did before, just work out Bose commutator relations, what you get is an equation which looks very much like we know for homogeneous magnetization precession. It looks like just a simple Lana-Richet equation, except that this product now is in hyperbolic space. So it has a minus sign for the third component. And now we also have a very direct idea, okay, what should be the effective torque? So this torque should then in the end determine the symmetry. And this allows us to then make predictions, or to describe at least what would be the symmetry that you should observe in these crystals. So this is what we did, and this is going to be one of the last slides. Like we understand now that you can actually calculate from this, from understanding that you have, that we should look at spin correlations. And that then means that we also think, okay, if that is your excitation mechanism, you perturb spin correlations, okay. If these are different, it means also that in your optical susceptibility, you have different terms on the diagonal. That means, and this difference xx minus yy is a direct consequence of these opposite phases that we have. So we get this cosine 2 alpha also for the geometry that I was showing. And if you have this pump-induced anisotropy, which is an induced anisotropy which can happen even if there is no spin-orbit coupling. So we get this polarization dependence, which is sine 2 beta. And here you see experimental results which were carried out by Alexei's group, which confirm that this is indeed the polarization dependence that we need. So this brings me to the end. So I think now we at least I understand that symmetry of two-magnon excitation should be understood in terms of exchange correlations which live on a bond. And we can have propagation of these magnons pairs, even supermagnetic propagation of these magnon pairs. And we have now an effective Lana-Richet equation or torque equation which allows us to understand the symmetry. And I think this is really an appealing approach to also look at not so highly symmetric antiferromagnets in which you, and in particular materials which you think are altermagnets in the ground state, and try to understand what kind of ultra-fast altermagnetism might be there. Thanks a lot. Oh, I should of course thank all the people that did the work and the funding.